Okay, logic and quantum computing. So this is a very vague title. To be more specific, I could say the multiplicative fragment of a particular logical system which I'll be introducing, which is linear logic. And then for quantum computing, what I really mean is quantum error correction. So quantum error correction codes, and I'll simply abbreviate that to QECC. So maybe I'll write this out once. And today's going to be a standard math style talk. This is going to be the pop music of math talks. So I'm going to give you two stories and then I'm going to relate them to each other. So one of them is going to be the story of quantum error correction codes, and one of them is going to be the story of multiplicative linear logic. These are both systems that have some kind of dynamics associated to them, and I'm going to be relating these two dynamics together. So I'm going to give you two pieces of maths, and then I'm going to relate them. So on the one hand, we have QECCs, and the dynamics is the process of error correction. On the other hand, we have multiplicative linear logic, and the dynamics here is a system of proof rewriting, which is referred to as cut elimination. And I'll be introducing that with more detail and with a proper explanation a little bit later. Okay, I'm going to start with the QECCs side of the story. And for this, I'm going to assume absolutely no knowledge of physics whatsoever. And in fact, I can't do any better than that because I have no knowledge of physics whatsoever. So if you're in the audience thinking I've got no physical background, then that's good. That means that you and I are on the same footing. So you can approach this purely mathematically just by taking certain things that are called certain things inside the physical literature, and then just referring to them as mathematical definitions. And then it's just completely up to you whether you go out and learn the physics that makes these suggestive names meaningful. But for today, they're just going to be definitions. So a qubit is simply going to be a copy of the C Hilbert space C squared. So C being the complex numbers. Very simple. And then a state of a qubit is going to be a vector inside a qubit of norm 1. And I'll be using Dirac notation. So this is simply notation for a vector. So this is an element of C squared. And for it to be a state, we require that it is of norm 1. We have a concept of measurements, and each measurement is going to be a family of operators from some Hilbert space to another Hilbert space, parameterized by some set M, and we require that these are satisfying so that's the adjoint operator to M sub M and composed with M sub M is equal to 1, okay? And so I've given this definition from the perspective of or in the context of a general Hilbert space, but we absolutely don't need infinite dimensionality for what I'm talking about today. It's much, much simpler than that. In fact, you can just think about the Hilbert spaces as tensor products of qubits. Okay, associated to each measurement is a value. Or a family of values parameterized by M. So we call this P of M, and it's simply the inner product when I've applied the operators N.
Could your daggers look like daggers and not pluses, please?
Oh, nice. Yeah, okay.
Just so.
Is that a dagger, or do you want some exotic?
No. That dagger was fine, but it has to not be invariant to rotation.
Okay. Okay. M sub M cross, also known as M sub M dagger. Okay, and this is notation for something familiar anyway. So you can just apply the operator M to the vector and then take the magnitude and square it. Okay, and then obviously we're thinking about this as like, a measurement is the measurement of some physical system. And we have this rough, vague idea from the pop culture of quantum mechanics that has been delivered to all of us, that there is some kind of impact that measurement has upon the system involved. And so that intuition is going to be fine for today. But to put some kind of precision to it, we're just going to say that there is also this thing which I give the mathematical definition of a resulting state, right? So I underline this because that's a definition. After measurement this guy, and outcome M is the following vector. So we apply that operator to the state psi, and then we divide by the square root of Pn. Good. So those are the basic definitions that I'm going to be using for the quantum error correction side. Now, what this has to do with error correction and the way that we use it and the way that we put all of these together is a story, and that story gives us the theory of quantum computing. I'm going to show an example so that we can get a feel for how these pieces fit together. So let me move over here. Man, I like the... Okay, so does the border around the boards imply to me where the camera can see or something?
It's where the camera's going to look if you stop moving. Yeah.
Yeah, no, that's a good idea. Okay, so let's have a look at an example. So first, let me just introduce some notation. So Z is going to be this matrix, and X is going to be this matrix. And we'll say that we started off with some vector psi, which is A, some complex number, multiplied by 0, 1, 0, plus B, 1, 0, 1. Okay, and then the way that you want to think about these vectors, 0 is, wait, which one is it? It's 1, 0. So this is literally just 1, 0 inside C2, and then 1 is just 0, 1, also an element of C2. So they're those two basis vectors. And then when you see something like 0, 0, that's shorthand notation for 0 tensor 0 inside the Hilbert space C squared tensored with C squared. So when you see three of those, that's inside the space C squared tensor C squared tensor C squared. Okay, so we need to assume that this is a state. So let's say this is a state, which is to say that it has not 1. So the magnitude of A squared plus the magnitude of B squared is equal to 1. The way that we're going to think about this state is that it's really the state 0, 0, 0, A times 0, 0, 0 plus B times 1, 1, 1, but it has had an error subject to it, and the error has flipped the bits in the middle. So you can see, so in fact, we can just state that psi is equal to x sub 2, which is equal to the identity. Okay, let me not be lazy with my notation. That's going to get confusing. Okay, so if I write something like x2, that's identity tensor x tensor I. That's an operator. So I could apply x2 to the following vector, a 0, 0, 0 plus b 1, 1, 1, and that is going to give me psi. Okay, so think about psi as that vector a 0, 0 plus b 1, 1, 1, which has had the error x2 applied to it. And so what we're going to do is try to discover that that is what the error was, and then we're going to fix that error. So the way that we do that is we first perform the measurement psi z1, z2 psi. And this is an explicit calculation. So this is a 0, 1, 0. Wait, I've written that out wrong. Oh, come back. Erase too much. Okay, so this is a 0, 1, 0 plus b 1, 0, 1, z1, z2, a 0, 1, 0 plus b 1, 0, 1. Okay, and then if we apply z1, z2 to this, then what we notice is that the vector 0, which is part of the, okay, so let's think about this operator acting on this vector, then z1, z2 applies z to this component, and then z to this component, and z applied to 0 is just acting like the identity, so it just gives back 0, but z applied to 1 is giving you back -1. So you can just look at this matrix and imagine that it has been written with respect to the basis that I wrote up here. And then you can get the action of z1, z2 upon this vector. So the result of that is that entire vector is multiplied by -1. And then the same thing happens over on the next component of the vector, which is this. So what this turns into is just the negative of psi. So that equals a 0, 1, 0 plus b 1, 0, 1 multiplied by negative a 0, 1, 0 plus, whoops, that's minus b 1, 0, 1. And then that ends up being negative a squared minus b squared, which is equal to -1. Okay, so that's the first measurement that we performed, and this is the first outcome that we got. So then what we want to do is check what the resulting state was. So I can just use the formula from before, and we see that z1, z2 psi over square root of p of m is equal to negative a 0, 1, 0 minus b 1, 0, 1. Okay, so that's the new state of the qubit. And then what I'm going to do is perform another measurement on this resulting state. So let me call that psi prime. And then what we do is psi prime z2, z3 against psi prime. And again, this is a calculation. So maybe I'll spare you the details, but you can just see that this comes out to negative a squared minus b squared, which again is equal to -1. Okay. So we performed two measurements and we got these two outcomes, -1 and -1. So now what we're going to do is just think about it. So we say, assume only one error occurred. Assume also that it was a bit flip error. And what I mean by bit flip error is it was x applied to one of the components inside the tensor product. So it was either x1 or x2 or x3, okay? So the possibilities x1 or x2 or x3, okay? And then what we want to do is say we performed z1, z2 to this vector, and we got -1. So that means that either the first bit was flipped or the second bit was flipped. And then we performed z2, z3, and that also gave us -1. That means that either the second bit was flipped or the third bit was flipped, okay? So either the first or second was flipped, and either the second or the third was flipped, and we know that there was only one error, and there was only one bit flip error. That just tells you that there's only one possibility. It must have been the second bit that was flipped. So then what we can do is perform this to the vector psi, and we'll be able to recover the original message, which is just some state inside a vector, inside the Hilbert space. So what we do is we perform well, what we really need to do is, okay, so what we really need to do is apply x2 to the vector that we get after the measurements that we've performed, right? But I suppress that part of the story. When you do this and you get the resulting vector, so psi prime over the magnitude of z2, z3, that's actually equal to psi again. So our measurements, the first one knocks it out, and then the second one actually fixes it. So now we can just perform x2 psi, and this will recover. This will recover our vector that we wanted. Okay, so that's an example of an algorithm being performed that does error correction for you in a very simple context. Okay, so now we can give a more general definition of what a quantum error correction code is. So a QECC is a pair consisting of a Hilbert space and a set of operators on that Hilbert space. Okay, and then in our last example, we had that S was equal to Z1, Z2, and Z2, Z3. And then the code space, which is the set of correct messages or correct states, are all of the vectors that are invariant under this set of operators. So think about these as the check operators. They check whether an error has occurred. And so if your vector ends up invariant under these, then you are a correct message. And if you deviate from it, then you've had an error occur to you. So h to the s is equal to the span of 0, 0, 0 and 1, 1, 1. And there's actual content there. That's not a definition. This is the set of vectors invariant under all operators in S. Okay. The AIs are incredibly talkative. Does anybody have a question in the chat amongst all of it?
No, you can ignore it.
I can ignore it? Okay, nice. Does anybody have any questions at this point? That's actually the end of the quantum computing part. So next is to talk about proof structures and then relate the two. So any questions on error correction? Okay, so do I go back to board one or do I move over here? Move over here, I think. Great. Now let's have a look at proof nets. So this is a system of logic. So I have to define what it means to have a formula, what it means to have a proof of certain formulas, and I'll start off by telling you what a formula is. So assume that we have an infinite set of atomic formulas. X, Y, Z, dot, 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 etc. And so these are just names, really. Okay, and then an oriented atom will be a pair consisting of an atomic formula as well as either plus or minus. And you want to think about these as the positive proposition or the negation, right? So just the proposition, the naked proposition or its negation. Nice. And then you can build compound formulas out of these atomic ones using connectives. So any oriented atom is a pre-formula. And then if A and B are pre-formulas, I'll just shorten that to PF, then A tensor B, and this next one's a bit of fun if you haven't seen it before. That's an upside down ampersand, and we call that par. Very hard to draw. Are also pre-formulas. And then if A is a pre-formula, then the negation of A is. Okay, and then formulas, true formulas are going to be quotient, so going to be equivalent classes of pre-formulas under just pushing negation through the compound formula. So what you do is you say equivalence classes of pre-formulas under tilde, and tilde relates tensor and par as follows. And then on the oriented atoms, it works like this. It just flips the polarity. That's the reason why you can think about plus and minus as negation and the positive. Right equals. Okay. Good. So there are most basic primitives, and then we want to build proof structures or proofs out of these, or proofs of formulas. And this is done kind of graph theoretically. So you have to be a bit careful with the way that this definition is constructed properly, but I'm going to satisfy us for today with a generating set of links, which are sub graph structures that you then build proof structures out of. A proof structure is built from the following links. So we have the conclusion link, That's a C down the bottom for conclusion. And then we have axiom / cut. Think about the axiom as from A, I can prove A. And then we've got the tensor and the par links. Okay, so the nodes of our graph are the connectives, and then the edges are labeled by formulas. Cool. So they're the building blocks, but it's probably not fully transparent what these things really look like. So let me draw out an example for you. So we could have an axiom coming into a tensor. And then that is getting cut against the par of the conclusions of some axiom link. Okay, so that would be an example of a full proof. So when I'm talking about a proof inside proof nets, it's something that looks like this. Okay. I promised you dynamics. So the point is that there is a cut elimination process. So if you have a proof that involves a cut, then you can reduce that cut, and you can reduce it continuously until you can continuously reduce it with lower complexity until eventually the cut disappears entirely. And so we're able to rewrite proofs that admit a cut as proofs that don't admit a cut. And that process, that sequence of proofs with lower complexity cuts, is the dynamical process of proof nets. So we have two generating rules for this. Right, so if I cut just straight against an axiom, then that reduces down to just as though I didn't have that axiom and I didn't have that cut. And then there's a symmetric one of these. So A cut negation A x A, that goes down to A. And then there's one involving the cut of tensor and the par. So if I go A tensor B, A tensor B, and then I cut against negation A, par negation B. Then this simplifies down to just directly cut the A with the negation A, and then same for the B. Okay, and don't be fooled by the right-hand side. This doesn't necessarily end you with a disconnected graph. So the point is there might be some connections up here that are preserved down here. Okay. So that's just a process that I can enforce upon you. I can just say, here is a logical system, here is an example of a proof, and if you have cuts, then you can perform these reductions, and you end up with a sequence of proofs that perform a process. There are reasons why this process is interesting, both from the perspective of computer science and from logic, but I'm not going to go into it right now. For now, you can just swallow the agnostic belief that this is a real structure. This is not an arbitrary thing. The reduction process can be understood in meaningful ways. Okay, so now I want to talk about relating the two. So maybe that's another good moment to pause. Did anybody have any questions about the proof part of the talk? Okay. So to relate the two, I'm going to start off with a proof structure and then associate to it a quantum error correction code. And then we're going to look at the two pieces of dynamics on either side and see how they're related to each other. So what we do is we look at the proof structure as a collection of links. So we say to each link, we associate a set of unoriented axioms. Unoriented. So in the axiom and cut link example, we have A and we have negation A, and then we have A and negation A in the cut case. Then we say A is some formula, and it's a compound formula that is built out of atomic propositions. So this really looks like x1 box 1 dot box tensor n minus 1 xn, where box I is either a tensor or a par link, right? So A is just some compound formula of atomic axioms and atomic formulas. And so what I can do is if I label these links L, so I've got some link, either an axiom link or a cut link, and I call that L, then I'm going to introduce this notation of square brackets L is simply equal to this set of unoriented atoms, so x1 up to xn. Okay, and if you're worried about duplication of formulas, then just take the disjoint union over all of these atomic axioms. So I can put the numbers down there in order to distinguish them, but that's not structure involved in the formula, that's structure involved in the way that I've defined this set. Okay, and then for tensor and par, we have a similar thing. So we have A coming into either a tensor or a par link, so that's A box B, where box is either tensor or par. And then I'll just use the same notation as above here for A, but we have a similar story for B as well. So Y1 diamond 1 dot 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 diamond M minus 1 Y M, where diamond I is either tensor or par, right? And then if this link is labeled L, then box L is going to be the set of all the formulas in A and all the formulas in B. Cool. And the reason why I've done that is so that now I can define a Hilbert space, which is going to be the exterior algebra of the complex vector space freely generated by these sets. That's going to be the Hilbert space associated to each link. And then for the entire proof, I just sum over all of the different links in the proof. So if I let L be the set of links of a proof pi, then the Hilbert space, or the total space of pi, is defined to be the wedge product of the direct sum of all the links inside L, and we take the direct sum of all the formulas inside the set of unoriented axioms of that link, and then we just introduce basis vectors for each of these. So that's the complex numbers multiplied by psi, which is some formal indeterminate, sub x sup L. Okay, and that is isomorphic to the tensor product over all L in L over all X in L of the wedge of C psi L X. Okay, and then I'll squeeze this in here. Just note that the wedge product of a one-dimensional complex vector space is isomorphic to c squared, okay? So what's been written down the bottom is this tensor product is truly a tensor product of a collection of qubits, okay? All right, let me go back to the first intervals. So now we have a bit of a clever moment. So since I've introduced the exterior algebra, there's in fact some extra structure which is lurking here, and we can take advantage of that to strengthen the relationship between the proofs and the quantum error correction codes. So let me talk in general for just a moment. In general, if V is the wedge product of some finitely generated free vector space, well, I guess the free finitely generated vector space, K, let's call it, then for each generator, theta I, there is a pair of maps, linear functions. And the first one will simply be denoted theta I, so that's an abuse of notation there. This is now theta I acting as a representing a operator. So that maps theta I1 wedge dot 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 wedge theta I d to theta I wedge theta I1 wedge dot 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 wedge theta I d. Okay, so it's basically just multiplication, right? And then the second one involves the dual element. So theta I star is the element of V dual corresponding to theta I, but this still maps from V to V. And it takes theta I1 wedge dot 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 wedge theta I d to this sum. So it's the sum from all j equals 1 up to d of -1 to the power of j minus 1, and then theta I star of theta I j multiplied by theta I1 wedge dot dot dot, and then you take out theta ij. So theta ij hat means that we have omitted theta ij, wedge dot 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 wedge theta id. Okay, so that one looks a little bit more complicated, but there's a reasonable sense in which this is simply the dual map to what is given previously. So there's a way that you can make this less scary, but having an explicit formula is going to be helpful for the next bit that I want to tell you. Okay, so then we have this lemma, and this lemma is what is going to relate these exterior algebras that we've associated to proof structures to operators x and z that I introduced at the start inside the quantum error correcting component of the talk. So I want to talk about bits and bit strings. So let's say I had a bit flip operator. So this is a map from this set, so in some n-digit binary number to itself, and it flips the ith digit, right? So it will send a 1 dot 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 a n to a 1 dot 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 a I bar dot 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 a n, where 1 bar equals 0 and 0 bar equals 1. Okay, I can go ahead and define that, and when I do, what we find is if I look at this operator theta I plus theta I star, okay, so those are the operators, not the elements, the operators, and I apply that to some element inside the exterior algebra V, so theta to the power of a underline, which is just some sequence of elements, it's just some binary sequence, then that is going to end up being equal to -1 to the power of a1 plus dot 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 plus a I minus 1 multiplied by theta to the power of bia. Okay, so theta I plus theta I star, think about that as a bit flip. So theta to the power of a underline is some sequence which is determined by the basis vectors that I started off with, and also the sequence that defines a. And what this operator does, it's just a calculation. You can just go ahead and do the calculation, but you'll find that what it does is it flips the ith digit in a. So there's also a sign, but we can work with those signs as well. The main point is the bit flip here. So we also have another operator, theta I minus theta I star, and this also performs a bit flip with a different multiplication factor out the front. AI theta B I A. Good. Okay, so now it's meaningful to define xi of theta a a bar to be equal to theta to the power of bi a, and then zi theta a is going to be equal to theta a bar if ai is equal to 0, and then it's negative theta a bar if ai is equal to 1. So think about these as the x and z operators that I wrote earlier. Cool. So we have rediscovered these matrices that were involved in error correction, but from the perspective of exterior algebras. Okay, and then we have a so let's recap at this point, because I now want to use this general theory to the proof, the total space of a proof structure. So what I've done is I've said, here is a proof structure, and here is how you extract a Hilbert space from it. But I only took into account the formulas. So I've just kind of freely generated some vector space over all of the formulas. The question is what happens to the edges, and we encode those edges inside the operators that are involved inside a quantum error correction code. So do you remember that a QECC involved two things, a total space and also a set of operators? Well, now I want to use what I've just explained to you, the general theory, in order to produce these operators that give rise to the QECC corresponding to a proof structure. Okay, so let's do that. For each unoriented atom U in pi, we define an operator theta sub U on H pi, which renders the following diagram commutative. Where U1 up to UR are the unoriented atoms of pi. Okay, so what we notice is that every such U exists in two different links. It's going to be, if you're inside an edge, then you're going to be the conclusion, but also the premise of some link, except for in the axiom and cut case. But no, sorry, it's also true in the axiom and cut case. So that's always true. The only time where it might not be true is in the conclusion links, but I didn't say it, but we just attribute the empty set. The conclusion links trivially contribute to the total space of a proof structure. So the point is that UI is is inside one particular link, and then UJ is inside another one, but they pertain to the same common unoriented atom inside a edge of pi. So we can just make the assumption that J is less than I, and U with orientation plus, and now I can finally give the diagram, but maybe I'll give it on the next, oh no, that's a bad place to do an export. Okay, I'll put it here. I can make it legible, but I'll use a different color to help. Okay, so we have this total space. Oh wait, those are tensors. And do the same thing downstairs. And then this is h pi proper. This is h pi proper. That's an isomorphism, that's an isomorphism. So this is just how direct sum can be pulled out of an exterior algebra where the sums turn into tensors. I mentioned that earlier. And then the left-hand side vertical arrow is xj, composed with z, j plus 1, dot, 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 up to z, I minus 1, x, I. So that's some operator. And then on the right, this is theta u, and that's the way that we define theta u, okay? And the point is that we do that for all of the oriented atoms u inside pi, and then we set s pi to be equal to the set of all theta u, with u ranging over all of the atoms in pi, as I said. Okay, so now we have truly attributed a quantum error correction code to a proof structure. We have both a total space and also a set of operators. So I've gone massively over time, but hopefully that's okay. I can wrap up very quickly.
Yeah, we should finish around 10, but you can keep going. Yeah.
I'll definitely be done in 10 minutes. That's okay. Okay, so that's now equal to h pi sub comma s pi. And then the theorem that actually relates these dynamics, or at least goes partway toward doing that, is as follows. So for a reduction gamma pi to pi prime, so these are the this is the proof theoretic dynamics that I gave you earlier, the reduction of the axiom cut length or the cut across the tensor and the par. So given one of these, there exists a subset C sub pi of S sub pi and an isomorphism gamma hat from the total space of pi prime to the invariant subspace of the total space of pi of this set C pi, so that for every g an element of S pi less C pi, there is a unique g prime an element of S pi prime, making this diagram commute gamma hat h pi c pi h pi c pi gamma hat h pi prime g prime, and the map g to g prime is a bijection from S pi less C pi to S pi prime. Okay, so you might be thinking, what's the point? The point is that I haven't told you what the definition of this isomorphism is yet, and that's really where the interesting part happens. So let's go back to one of these reductions that we looked at inside proof theory. So I'm just labeling the links here because I'm going to use them by name. And we know that that reduces down to something like this. then what we have is for each u y in A, if y is equal to positive, so I'll just give you the definition in the case where y is of positive orientation, but the definition when y is a negative orientation is incredibly similar. It's not incredibly similar, it's very similar. We have gamma u hat goes from wedge C psi u L, so that's the qubit pertaining to this link, to psi u L tensor psi u L cut tensor psi u L x. And what this map does is it maps a vector j to the following entangled qubit. The following entangled state of a qubit. -1j minus minus minus. Okay, so the map creates entanglement. And that's the way that smaller proofs are embedded into their bigger ones. So I'll wrap. Oh man, that's crazy. I just lost my pen. Oh, I just lost my iPad. Dan, could you please write up the following slogan, which is literally the final line of my talk. The slogan is proofs are patterns of entanglement.
Sorry.
Did you hear me? No. Proofs
please.
are, yeah.
Proofs are
patterns. Yeah, that's what I was saying. All right, got it. Thanks,
patterns
of entanglement. Or they encode patterns of entanglement. I mean, R is fine. Proofs are patterns of entanglement. Thank you. Good. That's the end of my talk. Thank you for listening.
Thank you. Well,
you're welcome.
Thumbs up.
Oh, nice. Oh, fine. Okay.
Questions for Will.
All right. It's been a long day for everyone, I guess.
Yeah, let's bring these guys back. See if they have any questions.
Yeah. Are they reading the board?
They can't read. Yes, they should be reading the board, I think.
Oh, interesting. I think they were all pretty bad. Same referring to.
Guys hear me?
Yeah.
I don't know if this even makes sense, but I'm kind of curious, like, has anyone done math with these proof nets? Like, it's supposed to be like a language for writing down proofs, but has anyone like actually proved anything with them?
Yeah, so there's a big long history of all of these proofs, all of these different logical systems and what their grounds are and why people were interested in them. So if you go back to first order logic or, Russell Whitehead type theory, then they were very interested in creating a foundation of mathematics and building maths off that. And that program was very successful in ways and very unsuccessful in other ways. But in the modern era, there's also this whole concept that a logical system is a mathematical object in itself, right? And you might want to study it for its intrinsic properties because it might have relationships to other areas of math, in particular computer science, right? So linear logic came very late in the game, and there are people that enjoy philosophizing over what a foundation of mathematics inside linear logic would look like, but it's a weak system in some sense, but it's very interesting as a system of computation. So I don't think that the literature is as interested in creating a foundation of mathematics using these particular proof systems, but people have tried to do that with neighboring systems of mathematics, for example, intuitionistic sequent calculus. There are a lot of similarities between intuitionistic sequent calculus and linear logic, especially on the level of their relevance to computer science. And people absolutely have tried to create foundations of mathematics off intuitionistic logic. That's where you get constructive mathematics and internal languages to certain categories and higher categories. So people have, but for linear logic itself, people are most interested in its relationship to computer science.
Thanks.
That
Yeah,
might be
besides
something.
like the intuitionistic stuff, like people actually tried to do math with it. So I was curious if anyone like actually did it with this or not.
There's
Yeah.
if you're looking for a particular instance, look up London Learning Lean or look up Kevin Buzzard, and that'll give you an idea of one way.
So there's a paper by Mike Schulman that explores how linear logic, how linear logic allows you to think more clearly about constructive mathematics, which it's not easy to do constructive mathematics actually. And Mike has an argument that the kind of funny connectives of linear logic helps you in doing that properly. I don't know much about it, but that seems like it's to do with what you're asking about. Let me treat you like an AI will and say, give me a summary of this talk in one sentence. Like, what is the
Okay.
what is the idea here? That,
Well, I did it at the end.
Yeah.
Proofs of patterns of entanglement. Okay.
Why do we
So-
care about making them out of patterns of entanglement? What are we getting out of doing that?
So robustness inside quantum algorithms or something. So you could understand the dynamics of linear logic as adding robustness to your quantum error correction, your quantum codes, because you're adding redundancy as you increase the cuts inside your logic system. So to put that into a sentence, I would say something like, you know what? I like that. Whoever said that. Understanding proofs as patterns of entanglement is interesting because, I don't know, we've drawn a relationship between two areas of mathematics. Understanding the nature of computation, creating a dynamic theory of mathematics. I feel like I haven't hit what you want me to say. Is there anything that you're fishing for?
No, not really.
I guess the way that I see it is, I've always seen semantics as trying to formalize the dynamical aspect of mathematics. So we have some logical system which we understand as a system of computation, and this system of computation could be completely meaningless. It might just be pushing symbols around on a page, and it might not represent anything non-trivial. So you look for a semantic system in order to get like soundness or possibly completeness if you were so interested, but kind of like a model has to exist as minimum for your system to be meaningful. And when you do that, you achieve extra things along the way. You also develop a computational theory of a certain area of mathematics. And if that area of mathematics is sufficiently complicated, then that's a helpful thing because it reveals further structure about that thing. So looking at quantum error correction codes, this is clearly a dynamical system, and we can understand that formally through the computational aspects of linear logic, for example. So it's kind of constructing a new status quo of like, here's your static math, but now we can look at its dynamic aspects.
Cool. Thank you.
Yeah, something like that.
I have a pretty hard hitting question.
Mhm.
In the context of Dan's earlier talk today, if AGI is coming in the next 10 years, why should we care about this project of understanding logic like to this depth at all if AGI is just going to answer all our questions and figure all this stuff out for us?
Okay, what's AGI?
Artificial general intelligence.
Oh, okay. That's
It's an easy one.
Well, do you mean it's an easy one?
No, I'm being sarcastic.
The reason why, look, like if you're gonna say, like what's the question, right? Like why anyone do it, including AI, or just why should we do it instead of just waiting around until the AI comes along and then ask it? That's the second one's a much more general question. And it's like, well, I think this is meaningful and it provides my life with value, so I want to do it for as long as I can. In the first case, the reason why anybody would want to do this is, well, my attitude towards mathematics is once you find something that is undeniably there in some sense, then you can only gain by studying it. So there's that whole debate that pure mathematicians don't have application, but I think that's just whether they find real math or not. I mean, this is getting very opinionated, but I think that there is a difference between actual structure and created structure. And I think that the created stuff tends to not end up being applicable, but I think that the real stuff ends up being stepped forward, but sometimes many years later. So whether we do that or AI do that, developing these strong connections between computer science, mathematics, and formal logic appears to be there. And so there's going to be something that comes from studying it. And so it's something worth doing.
But so what's the product or like the benefit for humanity at the end? Is it like just we get to marvel at beautiful things, or because it's hard to argue that it's sort of like furthering the well-being of humanity to work on this now if we could just like wait for AGI to do it and sort of work on AGI more to make it come sooner. Like, so is it sort of mostly a artistic enjoyment thing for you, or?
Well, I think that you have to sit down with yourself at some point and have a harder conversation with yourself and work out what your best chance at a meaningful contribution to the world is going to be. And it's not as linear as you make it sound. Like, AGI is going to benefit humanity greatly, and therefore everybody should work on it, is not good reasoning, I don't think. I think that those who have the skill and the passion and the opportunity and the talent should go for it. But I don't think that my most meaningful contribution could be to do that. Instead, the way that I could most positively give back to the world would be to work tirelessly on something that I genuinely see as special and important that I want to be, that I feel passionately toward. So maybe this is not the fastest way to go about obtaining the theory, and maybe it's not even the most effective, but it seems to me like this is the most relevant way that I could provide a meaningful contribution, because I don't think I'd be able to do as good a job work on AGI as I would be able to do here. So the rest of life after AGI has yet to be determined, and I've got opinions on that as well. We're going to have to shift our jobs into jobs that we want specifically human beings to do, and then use that as leverage in order to get pay. That's my one-line opinion on that. And maybe I'll do that at some point by turning this into an artistic endeavor that people want specifically a human to perform. But that's not the reason why I'm doing it at the moment. I'm doing it at the moment because I believe there's something there, and I have an agnostic belief that math is meaningful and it leads to good things. So here I am.